Assalamualaikum warahmatullahi wabarakatuh, and hi to everyone. So let us continue with the last part of chapter 2, particularly on the three-phase transformer. So this is one of the example of how three-phase transformer, the very large transformer or three-phase network transformer looks like over here. Then yes, this is basically located at the station, okay, the substation, the generation station, the transmission, distribution, etc. etc. So now we have the basic diagram or the representative diagram of the transformer, which consists of core as well as the winding. So in this particular diagram, so we have a three-phase Y to delta configuration transformer with three-leg iron core. So we have leg number 1, so we have leg number 2, and leg number 3. And we do have the capital A, B, C, which represent the star connection, and the small letter A, B, and C on the other side, which are representing the data configuration. If we can draw the Y or star configuration, it will look like something like this. Okay, so we have over here the A, so we have over here, so we have the B as well as C, so we have in between the N, right? And similarly, if you go down here, we have on the other side the delta configuration. So we have A, the small a, we have small b as well as the small c. And the configuration of the winding itself here, these three, we have a common point over here and being grounded, and this makes the configuration of star. Meanwhile, on the other hand, so we have the green color of winding over here. So the A, B, and C coil, and if we redraw the configuration, so we give you a delta form over here. Okay. Now, the usual connection for three-phase transformer. So basically, we have few or multiple possibility for the connection, whereby we start with the star and star configuration. So this is seldom used due to the imbalance condition and the third harmonics problem. So we have especially the load imbalance that result in the voltage on phase become severely unbalanced. And what about the third harmonics? So what it cause? It may cause the increasing current in neutral conductor. So this is the reason why the problem we are facing with the third harmonics issue. All right. So then the second one is here. If we have some improvements and we have some modification, we have the YY delta. So this is frequently used to interconnect high voltage networks, for example 240 kV, okay, down up to 345 kV. So the delta winding over here is to filters the third harmonic. So this is the function of this data interconnection. Okay, so we may filter out the issue of third harmonics and equalizes the unbalanced current. Then this means we try to stabilize the unbalanced currents between the phase and provide parts for ground current. Of course, for safety measure. And then the third one is a star delta configuration. So again, this is frequently used as a step down transformer, for example 345 kilovolt down to 69 kilovolt, and followed by delta to delta configuration. This is used for medium voltage around approximately 15 kilovolt. One of the transformer can be removed or open delta. So one side of the transformer actually. And then last but not least, the delta Y configuration. This is particularly applied in the step up transformer, especially in a generation station. So first, the YY configuration, the line voltage of primary and secondary related to phase voltage is given by. This is how we actually relates between the line voltage of the primary and secondary by having this equation. So we have V phase of the primary side, which is equal to the V line of P over square root squared. Or in the other way around, we may write that the line voltage of the primary, this is equal to square root 3 the phase voltage of the primary side. And then similarly, we have the VL, the line voltage secondary. This is equal to square root 3 V phase primary. Okay. So it happens at both sides, primary or secondary, because we are subjected to star configuration. Okay, whereby the I line, for example, primary. So this is equal to I phase primary. So similarly for I line secondary, so this is equal to I phase secondary. Okay. So this is some of the conditions, the rules and regulations when we talk about star configuration. Okay. So some, but the advantages, the disadvantages is the drawback of unbalanced currents and also the third harmonics. Okay, especially at the load. Okay. So again, the YY configuration. So this is how the diagram looks like. So we have a star on both sides, primary and secondary. Okay. And the turn ratio over here, A equal to NP over NS. So this is nothing but square root 3 VEN over square root 3 VAN. So both identical, because again we have star to star or Y to Y configuration. So this is for phase voltage and this is for phase voltage. Don't forget to multiply by square root 3. Okay, square root 3. If we represent the turn ratio in terms of line, so same goes to here. So we have VAB the line and VAB for the the other side of the line voltage. So we have VAB as well as the VAB. So just now the AN is over here between the phase A and also the neutral line, the common point over here, and line A, phase A for example, and also and common point, okay, the VAN. So this is how we analyze in terms of A, the turn ratio. So IA for the line current, so no problem. So we have IA. Okay. It's either line or phase. So there's no difference. So what about the Y delta configuration? So the primary and secondary line voltage related to phase voltage is given by V phase equal to V line over square root 3. So for the primary side, because we have Y over here, all right, so Y over here, and then we have this relationship. So what about the delta? So the delta is V phase equal to V line. Okay, so this is for especially for delta. Okay, so we have V phase which is equal to V line. So how about I line? So line is equal to, okay, sorry, line, this is equal to square root 3I like this. Okay, only for delta. So the delta windings filter the third harmonics. So this is some of the advantage of the delta winding or the delta configuration. So you may able to filters or to eliminate the third harmonics that give the uh, increasing current, especially the one flowing in the neutral conductor, and equalize the unbalanced currents and provide a path for ground currents. So the secondary voltage is shifted by 30 degree from the primary voltage. So again, still on the diagram, okay, the first of the star delta configuration. Okay, so let's look at the relationship in terms of the turn ratio. So we have NP over NS, no problem over here. But once we come to the phase, now we have VAN. So this is the phase for star, and this is the phase for delta. Because for the delta, V phase equal to V line. So VAB over here is actually V phase. Okay. So this is the V phase of the delta. Okay, this is the V phase for the star, and IBA over IA. All right, so IBA, this is again for the here this one. All right, so the phase current and also the line current over here. Okay. For the star configuration. So VAB, again, this is a VAB. So this is between line voltage and V over AB over here. Alright, so VAB over here. Okay, so this is for line voltage. So no problem, because again, I repeat, the line voltage and for the phase voltage for delta is similar. Okay. So this is equal to square root 3 Vn. If you try to convert to phase from AB, the line voltage of star, so you need to multiply by square root 3. But for delta down here, so you can simply use the same value of VAB, because V phase equal to V line over here equal to V phase. Thus giving us the relationship of A equal to square root 3A. Alright. And then star delta configuration the other way around, or vice versa, because we have star delta and then now we have the delta star. So in terms of the analysis, so it doesn't, I mean, so you just put it the other side or the other way around in order to understand the uh, equation, the relationships, and all associated with the configuration. So the primary and secondary line voltage related phase voltage is given again. So this is for the delta side. Okay, we have phase voltage equal to line voltage, and this is for star configuration. So we have phase equal to square root 3V line. Okay. So secondary voltage lag 30 degree from the primary voltage. So star delta, so how it looks like. So this is for delta, so this is for star. So always come with common point and grounded, so the so-called the neutral point. Okay. But no for delta. Make sure once you draw or you redraw the configuration, so there is no end point or common point for delta. So VAB over VAB, so this is for delta configuration over here. This is AB. Okay, so it doesn't make any difference between line and also the phase here. The VAB and also the VAN. This is for this point. I mean for the star, and V over VAB. Alright, so this is between line to line, the line voltage. And once you convert into phase, so make sure you multiply by square root 3 as shown over here. Okay. And this is nothing but E over square root 3. So about the data configuration, the primary and secondary voltage related to phase voltage. So no different. So we have V phase primary equal to V line primary, and we have V phase secondary equal to V line secondary. So transformer has no phase shift associated with this connection and no problem with unbalanced load or harmonics. Alright, so data configuration, how the diagram looks like. So yes, this is at the primary and this is located at the secondary. So A equal to NP over NS. So VAB over VAB. So this is for data and this is for data, both for data. So IA over here and also here IA. Alright, so this is for the comparison. IBA here, this is for the phase current as well as the phase current at the primary. It's a very direct forward relationship between the quantity of primary side and secondary side. Again, thank you very much for watching. Hopefully you have learned particularly the chapter number 2 on the transformer. And until next time, have a nice day. Signing off.